Good morning, physics class, and welcome to problem set 34, day 2. I hope that you're still doing well under these conditions. Miss having you guys in class, but I hope you're being able to keep up on your homework. So we're going to start off with this week's lesson, which is on specific heat, heat of fusion, and heat of vaporization. So I'm going to go back to the ice to steam problem that we worked on yesterday. And we're going to do this problem again as review to help you begin to understand what's going on. So the problem here that we want to do is we want to find out the amount of energy needed in joules to take an ice cube and turn it into steam at 101 degrees. Now, as we look at this particular problem here, you'll see we got a good chunk of ice, 2.1 kilograms of ice. So you guys know by now that in order to look at that in terms of pounds, you divide that by 0.454. So this is 4.6 pounds of ice. It's a pretty good chunk of ice. And we're going to try and convert that into steam this morning. And so there are some things that we need in order to perform this problem. And we need the specific heat, of ice, the heat of fusion, for ice to water, and then we need the specific heat of water, we need the heat of vaporization, then we need the specific heat of steam. Now, water is a very, very interesting and unique substance. It has a very high specific heat, which makes it so that it doesn't change temperature very easily, which keeps our planet under very, very stable conditions. So let's begin to talk about some of these things. The first thing that we want to look at is the specific heat of ice, which is 2050 joules per kilogram Celsius. Heat of fusion of water is 334,000 joules per kilogram. The specific heat of water, 4,186 joules per kilogram. It has a very, if you look at your chart, you'll see that there's nothing on the chart that has even close to a similar specific heat as that of water. Again, that's what makes our planet's environment so stable. And we also want to look at the heat of vaporization of water. And the heat of vaporization of water is 2,256,000 joules per kilogram. 2,256,000 joules per kilogram. And the specific heat of steam is 2,000 joules per kilogram Celsius. And this should have had a Celsius too on the specific heat of water. And this is the specific heat of steam. So now we can begin putting in what we know. And in this particular problem, we know that we have 2.1 kilograms of water. And we're going to raise the temperature of the ice 5 degrees to its fiducial point at 0. So if we started at -5, we want to get it up to 5 degrees to its fiducial point. So now what we're going to do is we're going to take this specific heat of ice, multiply it by the mass of the ice, and multiply it by the temperature we'd like to raise it to. And so we'll have 2050 times 2.1 times 5 to get the joules needed to change the temperature of the ice to 21,525 joules. Okay, the next thing we want to do is we would like to find the heat of fusion. So again, this time, simple unit analysis will just tell us that we got to get rid of the kilograms on the bottom, like so. And up here we canceled the kilograms and the degrees Celsius. So we take our heat of fusion, 334,000, and multiply that by 2.1 to get 701,400 joules. The next thing we want to do is we want to change the water temperature up to 100 degrees. So we'll multiply it first by the mass of 2.1 kilograms. That eliminates our kilograms, but you can see if you're doing the significant digits properly that you also need to eliminate the Celsius from the problem. And so we're going to go between the fiducial points of water from 0 degrees Celsius to 100 degrees Celsius, its boiling point. And so when we do that, we get 4,186 times 2.1 times 100 to get that it takes 879,060 joules in order to raise the temperature of water, that amount of water, 4.5 pounds of water. It takes that many joules to raise it from 0 degrees Celsius to 100 degrees Celsius. So the next thing I'd like to do is I'd like to vaporize this water through boiling, sublimation, whichever way you want to do that. So I'm going to take that, I'm going to multiply it by 2.1 kilograms. Kilograms are eliminated from the problem. So we'll get 2,256,000 joules times our 2.1 in order to get 4,737,600 joules. Again, I said this yesterday, I'll say it again today. Part of this problem is to realize that in the process of converting an ice cube to steam, the majority of the energy is found in the boiling process, in the vaporization process. So then in order to convert the steam to 101 degrees, we're going to have to take 2.1 kilograms and multiply it by 1 degree Celsius. That eliminates our Celsius from the problem and our kilograms from the problem. And so now all we have to do is take 2009 and multiply it by our 2.1, and we get 4,218.9 joules. Okay, so now we'll add up all the values that we have for the energy, the heat energy that it takes to raise the temperature of this water. So I'll take 4,218.9. I'll add 4,733,600, and I'll add 879,060, and I'll add 701,400, and then I'll add 21,525 to get a grand total of 6,343,803.9. I look back to the problem, I see two significant digits, so I'm going to say my answer is 6.3 times 10 to the 6th joules. Okay, I hope you're beginning to get this a little bit more, feeling a little more confident, so that come Friday when we have our quiz, you'll be all prepared for this on the quiz. Another problem that you'll probably see on your homework and on the quiz this week is angular acceleration and angular displacement. So in a problem like this, it's important for us to understand a few things. One of them is that angular acceleration, which we'll call alpha, directly correlates with linear acceleration. In the formula, A equals R alpha, or linear acceleration equals the radius times angular acceleration. It's very similar to the fact that linear velocity equals the radius times angular velocity. And so as we start this problem, we want to pay attention to some things. The first one is that it says here, Philip pedals his bike so that he accelerates at a constant rate of 0.33 meters per second per second. So I'm going to say that that's his linear acceleration is 0.33 meters per second squared. And it says that he has, find the angular acceleration, so we're going to be looking for alpha, and that the radius of his bike is 0.47 meters. That's a pretty big bike wheel if you ask me. And find the angular speed of the tires after 7.5 seconds if the initial angular speed is 3.1 radians per second. And what was the Tucker's angular displacement after 7.5 seconds? So the first thing that I probably want to do is I want to find the angular acceleration. So let's begin working on that with what we know already. So we have 0.33. The linear acceleration equals the radius of the tire, 0.47, times the angular acceleration. So I notice everything already is in meters, seconds, and meters. So I don't have to do any unit analysis to begin the problem. But what I'm going to do is I'm going to take 0.33 and divide by 0.47 to get the angular acceleration. The number I got in my calculator is 0.702126766. But the units become very, very important to what we're working on here in this particular question. When it says that we're finding the angular acceleration, what's our unit going to be? Is it going to be in RPMs or radians per second? Well, if we're in the metric system, it's going to be in radians per second squared. Revolutions per minute is not in the metric system, but it's usually what we're familiar with when we talk about these types of things. All right, so that kind of tackles part A, but part A is going to be very useful when we get into part B of this question. It says find the angular speed of the tires after 7.5 seconds if the initial angular speed is 3.1 radians per second. And this begins to sound like the motion equation. Now, we've talked about the motion equation this year in terms of just straight up linear terms in velocity final equals velocity initial plus acceleration times time. We can convert that into an angular version by saying that final angular speed is equal to the initial angular speed plus the angular acceleration times the time used. They're essentially the same thing, but one of them is talking about in terms of angular speed, the other one's talking about linear speed. So if we're looking for the velocity, angular velocity of this tire after 7.5 seconds, what we're going to do is we're going to talk about the initial angular speed of 3.1 plus the angular acceleration of 0.702126766 times the time of 7.5. I hope that you've understood that I got the angular acceleration from the previous problem. And so now we can begin working on the angular speed. So we're going to take our angular acceleration and we're going to multiply it by 7.5. That gives us a value of 5.26596. And we're going to add that to the 3.1 of the initial angular speed. And that ought to give us our final angular velocity. So I'm going to add 3.1, and I'll get my final angular velocity as being 8.366 radians per second. And I'm looking up here at the problem again. It says find the angular speed of the tires. It's not asking it in terms of revolutions per minute, so I'm just going to leave it in radians per second. Everything up until this point has been done in the metric system. I would like to keep it that way if at all possible. So the next thing we're going to work on is the angular displacement. And just like in the previous part of this problem, I'm going to go look back to my linear terms that we've already talked about, and I'm going to derive an angular equation for displacement. Well, I think the final change in my angle, which we'll call theta, angular change, is going to be found by the angular acceleration times the time squared divided by 2. Acceleration times time squared divided by 2. We've worked on that a lot. Plus angular velocity initial times the time plus the original angle of the bike. It doesn't give an original angle of the bike, so we're just going to zero that out. And so for the rest of the problem, we'll just put in what we know for 7.5 seconds. The angular acceleration is 0.7021, rounding that a little bit. Then 7.5 is the amount of time that we have. We're going to divide that by 2, and the initial angular speed was 3.1, and we're going to multiply that by 7.5. And again, our initial angle is 0. There wasn't one given to us in the problem. So what I always like to do is I always like to stick to, especially to help students out as much as I can, to stick to order of operations. So in my next step, what I'm going to do is, the only thing I'm going to do is I'm going to square the 7.5. 56.25 divided by 2 plus 3.1 times 7.5. Okay, now what I'd like to do is I'd like to do all my multiplication and division. So I'm going to take my 56.5, I'm going to multiply it by 0.7021, and then I'm going to divide that by 2 to get 19.747, because I'm looking for the angular displacement after 7.5 seconds. I'm going to take 3.1 and I'm going to multiply it by 7.5. When I do that, I get 23.25. I think that other line there is just an accidental touch of the screen. And then we're going to add those two values together. We're going to take our 23.5 and we're going to add 19.747 to get our angular displacement after 7.5 seconds as 42.997 radians. Again, everything is in the metric system, so we're going to use radians in seconds instead of miles per hour or revolutions per minute or whatever along those lines. So I have 3 solutions now. I'm going to take into consideration my significant digits. Look back, I see 2 significant digits, 2, 3, 2, 3. 2 significant digits in the problem. So my answer to question A is that the angular acceleration equals 0.70 radians per second squared. After 7.5 seconds, my answer to question B is that the final angular speed is equal to 8.4 radians per second. And my answer to question C is that the final angular displacement after 7.5 seconds is 43 radians. Okay, so that should solve our problem there. I'd be ready for this on homework and on Friday's quiz. As we move forward, The next question that we have is, it says that we have a 21 kilogram block that hangs on a rope that passes over a massless, frictionless pulley and is connected to a 14 kilogram block resting on a 67-degree inclined plane that has a coefficient of kinetic friction of 0.312. Find the acceleration of the blocks and the tension in the rope. You know what the first and best thing to do in a problem like this is? It's to start off with a free body diagram. So why don't we begin with that? Place a free body diagram here. Get our inclined plane. That looks like a good approximation of 67 degrees. We'll get our pulley system up here. We're going to have a block hanging off. It says that the block hanging off is the 21 kilogram block. And then there's a block on the inclined plane that has 14 kilograms. And this problem includes friction. We have a coefficient of kinetic friction of 0.312. All right, as I begin to look at this particular problem, the first thing that I'd like to do is I want to know which, it's going to be imperative that we know which direction the block is moving. So let's compare the force of what's heading down the plane and the force of the block that's hanging in free space. The force of the block heading in free space is found by mass times gravity. So it's just 21 times 9.81. Now, what's pulling to the left is going to be 14 times 9.81 times the sine of 67 is going to be pulling to the left. So let's compare the two. We've got 14 times 9.81 times the sine of 67 is 126.42. And we're going to compare that to 21 times 9.81, and we get 206.01. So we can see that the block is moving towards the 21 kilogram block. So we can begin looking at our forces now. We know that this is moving down, so we have mass times gravity, and opposing it is the tension in the rope. We know that this block here, we have the tension heading in this direction, and that's going to be positive heading up. And then we have Fx opposing it, and that's going to be negative. And then we have the force of friction, which is opposing that. So we have our force kinetic opposing that. And so this right here is going to be our force kinetic. Our force of x, force of x. And what I'd like to find out is my force kinetic. And so how I'm going to find out my force kinetic is that it's equal to force normal times the coefficient of kinetic friction. Well, we know that the coefficient of kinetic friction is 0.312 from right there, but we need to know force normal. And so force normal is going to be calculated in this problem by 14 times 9.81 times the cosine of 67 degrees. So we can calculate that on our calculator. 14 times 9.81 times the cosine of 67 equals 53.6630 newtons equals force normal. That will allow me to find force kinetic, because force kinetic is force normal, which is our 53.66, times our coefficient of kinetic friction, which is 0.312. So you plug that into our handy dandy calculator, and we get force kinetic equals 16.74 newtons. So now I have force kinetic, I have force of X, I know that's I know tension, I know mass times gravity from the other side there, so I can begin setting up a system of equations. So let's begin to work on that. So for the 14 kilogram block, my system of equations says it's positive tension minus plus Fk, excuse me, minus Fx equals mass times acceleration. Newton's second law says the sum of the forces in any direction is equal to mass times acceleration. So I'm going to have tension plus, we found out Fk is 16.74, and then Fx, which is heading to the left and down, so either way we look at it, it's going to be negative, is 126.42 equals mass, which is 14 times acceleration. All right, that ends up giving me a value I can solve for, t. So I'm going to take 16.74, I'm going to subtract 126.42, and so I'll get t minus 109.677 equals 14a. I can add that to the other side. T equals 14a plus 109.677. Now we'll begin working on block number 2, the 21 kilogram block. The forces here are a little bit easier. We have positive tension minus mass times gravity equals mass times acceleration. Tension, we don't know. Mass times gravity, we already calculated right here to being 206.01 equals the mass of 21 times the acceleration of the block. All right, we're going to add that to the other side. T equals 21a plus 206.01. Now we're going to substitute in t from our first problem. So it's going to be 14a plus 109.677 equals 21a plus 206.01. I can now begin to solve for acceleration. So what I want to do is I'd like to get all the a's on one side. And if I move them over here, we get negative 7a equals, I'm going to take 206.01 and I'm going to subtract 109.677 and I'll get 96.33. I'm going to divide by 7 and I'll get a equals negative 13.76 meters per second squared. Now I can plug that back into here to find the tension in the rope. So T equals 14 times negative 13.76 plus 109.677. So 13.76 times 14 equals negative 192.66 plus 109.677 equals the tension. The tension equals negative 192 plus 109.677 gives me 82.989 newtons. So when it comes time to finding the tension And the acceleration will apply significant digits of, remember I said earlier, I'm not really worried about degrees in significant digits earlier in the year, so I'm going to go with 3 significant digits. I'm going to have my tension as 82, excuse me, I've got to round that up to 83.0 newtons, and acceleration equals negative 13.8 meters per second squared. All right, let's move on. One more problem for today. An ideal gas is heated from T equals 65 degrees Celsius to T2 equals 102.5 degrees Celsius. Convert these temperatures to kelvins, and if the volume of the ideal gas is held constant and the initial pressure is 0.640 times 10 to the 5th pascals, find the final pressure. So over here I've got kind of a little GIF talking about the combined gas law. The combined gas law takes Charles' law, Boyle's law, and Guy Lussig's law and combines them into one. And in this particular problem, one of the concepts I really want you to get is it says in this problem with this ideal gas, the volume is held constant. So if you look here, the one that doesn't worry about volume out of these 3 gas laws that we have over here is Guy Lussig's law. You'll see there's no volume there. So we're going to be focusing on Guy Lussig's law today out of these 3 laws that make up the combined gas law. So what we'll do is we'll first start, it says right there, convert the temperatures to Kelvin. So we're going to take T1, which is 65, and we're going to add 273.15, and we're going to take T2, which is 102.5, and we're going to add 273.15 to get our kelvins in both cases. So we'll do 273.15 plus 65 to get T2, T1 as being 338.15 K, and these were degrees to begin with. And then we're going to find T2 by taking, T2 by taking our 102.5 and adding 273.15 to get T2 as equaling 375.65 Kelvin. All right, so now we'll use Guy Lussig's law today to say that the first pressure, the initial pressure, is 0.640 times 10 to the 5th pascals. And we're going to divide that by the first temperature, which was 338.15 Kelvin. And that's going to equal our final pressure. If our final temperature is 375.65 K. One of the concepts that you're supposed to get from this problem is you're supposed to see, is there a direct variation between pressure and temperature, or is there an inverse variation between pressure and temperature? If it's a direct variation, when the temperature goes up, so will the pressure. If it's an inverse variation, if the temperature goes up, the pressure will drop. Based on your knowledge of direct and inverse variation, something we've talked about a lot in physics class this year, we've talked about it in both math classes, is what is going to happen to the pressure? These are the 2 options, as the temperature increases, does the pressure increase, causing a direct variation, or as the temperature increases, does the pressure decrease, like that, which would be an inverse variation? Which one do you think is going to be the solution? So let's begin working this out. We're going to take our Pressure of 6.4 times 10 to the 0.64, times 10 to the fifth, 64,000 pascals. Do you know what the normal atmospheric pressure is? This is a lot lower than normal atmospheric pressure. Kind of let you think on that. You can Google that if you want to know what the normal atmospheric pressure is in pascals. We've talked about it before this year in class, but just testing your knowledge to see if you know what it is. So if I cross multiply the 375.65, we're going to get 24041,600, 24,041,600, and then we're going to divide by 338.15 to get our final pressure. So we'll divide by 338.15 and we'll get 71,097.44196 pascals is our final pressure. So when we begin putting in our significant digits into the problem, we're going to get 0.7. Let's see, we had 3 significant digits in the problem, so 711 times 10 to the fifth, or probably the better way to write that would be 7.11 times 10 to the fourth pascals. The reason I put this particular answer here was to compare it to the original question, and I don't want to circle that because then you'll think that's the answer. But when I compare these two numbers right here, did the pressure go up or did the pressure go down? Well, you can see there that the pressure went up, meaning that this is a direct variation. And Guy Lussig's law says that temperature and pressure are directly related. When temperature goes up, so will pressure. That's the lesson that we have today. Hopefully you're taking notes on this stuff, putting a lot of this stuff down, working on your homework, preparing for Friday's quiz. Have a great day. See you later. Thank you. Have a good night. God bless.